the question inside Microsoft was never, can we build a GPU? The question really is, like, what do we need to build the best AI infrastructure for this era of AI?
Hello, listeners. We have a special guest today to discuss Microsoft's Maia 200, their AI inference chip that was announced earlier this week. Welcome, Saurabh Dighe, CVP Azure Systems and Architecture. Thanks for coming on to chat with me.
Oh, it is a real pleasure, Austin. Thank you for inviting me. I'm happy to disclose Maya and happy to take any questions you may have.
Awesome, great. Okay, so I want to talk a lot about the why behind Maia, from business decisions to why make custom silicon, and then of course the why behind the technical trade-offs, because I think those are interesting and communicate something about what you're prioritizing and what you're not. But first, how about a quick refresher for anyone who missed the Maia 200 announcement? What's it all about and who's it for?
Yeah, no, great. So I'll just start off like we have been on this multi-generational silicon journey at Microsoft, right? We know that our customers want a leading AI infrastructure. And one of the things that we have to do when we develop leading AI infrastructure is have the freedom to innovate across every layer of the stack. So silicon is a very important part of this aspect. And so just yesterday, we announced Maya 200, which is our second generation of AI accelerator. And we'll be happy to go into a lot more detail with you as the podcast progresses. But this is really targeted towards, performance leadership for inference. So performance per dollar and performance per watt leadership for inference. We made very deliberate architectural choices, and we said, hey, we really need to make sure that as this wave of AI adoption and as more and more customers and the world starts using AI, inference economics is going to be a big important reason to invest in silicon and systems. So that's what Maya 200 was all about. It was really to drive the best AI infrastructure for us and meet the customer at the highest performance layer, but also at the lowest cost point.
Okay, yes, let's dive in there. So you talked about designing for your customers, and you're thinking about uh, TCO and performance. So when most industry observers talk about custom silicon, they frame it as a margin play traditionally. Oh, build your own chip, cut out the middleman's markup. But you're talking differently about Maia as, and I saw the blog too. There was, you had a nice post, and EVP Scott Guthrie had a nice post too. And it talked a lot that you both talked a lot about working backward from what your customers need with
Right.
respect to those metrics you mentioned. And so, yes, let's take it from that angle. Like, what are customers asking for that today's GPU fleet might not deliver for them?
Yeah, no, that's a great question. See, um, the question inside Microsoft was never, can we build a GPU? Right? The question really is, like, what do we need to build the best AI infrastructure for this era of AI? And if you take it from that lens, right, it starts becoming obvious that AI inference is actually a frontier efficient, it's a curve. And you have to be able to deliver real world capability and accuracy at different points in the curve, different latency, cost, and energy points. And so when we looked at it as a portfolio, we knew that it was not about one size fits all. It's really about making sure that we have infrastructure that's heterogeneous because we are embracing this multi-model, multi-use case scenarios where we have, certain use cases that could be super latency sensitive, right? If you're coding or if you're running copilots, a highly interactive environment, you're going to look for, extremely low latency applications. On the other hand, if you're, batching inference, you're doing some summarization, and it's okay to take some time, but more important, it is about throughput and cost at what you deliver. That's a different use case. That's a different model that you're going to be using, and there's probably a spectrum in the middle. So we look at this as, inferencing is not a one point solution. Inference is, there's a frontier efficient curve, and we need to make sure that our infrastructure is not about one size fits all. It's about delivering the customer the choice and the flexibility that they need to be able to deliver the inference workloads. Now, that's just one aspect to it, right? And now you say, hey, but I need to run this at planet scale,
Mm.
right? So then you go in and say, hey, the core principle about building Maya, or in fact any custom silicon for us, whether it's Cobalt, Maya, or Azure Boost, integrated HSMs, we have a portfolio of custom silicon now in Azure. The core principle here is that when you do full stack innovation across software, across data center infrastructure, about rack scale and network infrastructure, you're actually able to unlock a lot more efficiency and customer experiences, right? For example, availability is a big customer experience in the cloud, right?
Mm.
So not only in every region, but also the uptime that you can deliver, the ability to deploy it globally, the ability to find the right telemetry from your systems and integrate that back into the control plane. So these are all things that helps you kind of really innovate across the entire stack. And that's why I think that, it kind of comes down to, hey, do we meet the customer where they want to be met? Do we have that freedom to innovate? Do we have to deliver the economics and the cost point? And then also control our own supply, because this is going to be a big portion of our fleet. So the ability to manage capacity and supply becomes an important consideration as well. So that's how we kind of try to do this holistically across the entire, value proposition of building custom silicon and custom systems for Azure.
Sure. Yeah, and custom systems, that's a good framing, and especially when you're talking about innovating up and down the stack, not just with the AI inference chip, but CPU networking and so on. You talk about enabling this efficient frontier for workloads, some that might need ultra low latency, or some that maybe don't need that and just high throughput, large batch size. So talk to me, like, who are those customers and what are those workloads that you guys were designing for?
Yeah, yeah, that's a great question. I'm gonna refer back to like what Satya said, like Jevon's paradox. Like if you build the right infrastructure and continue to drive the cost down, you see more and more adoption. You actually are able to see more consumption. And I'm hoping that the way we build our infrastructure, it actually eases customers into driving more and more use cases. So like you asked me, what are the customers or what are the uh, key points and areas of our optimization? I think where we look at it is obviously when we designed Maya 100, we were in the era of CNNs, right? Convolutional neural
Mm.
networks, but we obviously moved to large language models and LLMs. And so we designed Maya to be really inference optimized for these large reasoning models, chain of thought. Some of the use cases that we are looking at is if let's say you're training a frontier model, and we're working very closely with our Microsoft Superintelligence team, like you still need a lot of inference in training loops, right? So how do you provide that inference at the right capability, but also at the right cost point? Is a great use case for us. When you run something like copilots, right, you have different use cases in copilots. You have use cases where you have to really sometimes go down to, time to first token could be less than a second, or it could be up to 10 seconds because you're just doing a summarization of a meeting that just happened.
Mm.
And so that gives you a little more flexibility. So we've designed the architecture taking into consideration how do we design for large language models, how do we design for Microsoft use cases that we know are kind of growing with our own in Microsoft Superintelligence team, with our Copilot offerings, as well as with Microsoft Foundry offerings. So those are some of the optimization points as you see in the architecture. And one deliberate choice that we made was we didn't pursue training as a first step. We knew that if we had to go pursue and make a system that was both training and inference, we would be adding a lot more cost into the system. We'd be adding a lot more inefficiencies from our point of view into the system, because we are trying to do something that is much more than what a customized, more optimized system could be able to do.
Sure. Yeah, that makes sense. I actually like that you guys just focus on inference because, as we'll get to in the technical trade-offs, we can really see the decisions that you made are definitely tuned for inference specifically. Um, okay, backing up a tiny bit, you mentioned Maya 100 was sort of designed pre-GPT, more for like CNN era, and Maya 200 was designed with large models in mind and even with reasoning in mind. When were you guys starting to put pencil to paper on the Maya 200?
Yeah, no, that's a great question because silicon takes a long time.
Yeah.
But we have, like, think about it this way, like we have a research team that looks ahead and looks at what is the evolution of the models. We look very closely with you know, our models team, we have data science team looking at new data formats, and then we have an architecture team that has to now could put it on pencil and paper. So you're right. I mean, around the year 22, 23, we kind of started really focusing and making a much more concrete proposal of what a Maya 200 would look like. And at that time, we had good information on how the architectural is shifting, right? So if you, for example, you brought up Maya 100, it was definitely designed with CNNs in mind, which is basically this is dominated by convolution layers. The data is much more local. There's much more dense operations going on. There's not a whole lot of focus on how much HBM bandwidth. In fact, my 100 I only had 64 gigabytes of HBM capacity. And then when you looked at it from an LLM standpoint, we said, oh, look, wait, I do need to change the shape of my compute, right? I do need large matrix multiplications. I do need more horsepower in SIMD operations. I do need a much bigger HBM bandwidth. So we moved to HBM3E. We moved to TSMC N3 technology for us to change the computation flop. We actually added 216 gigabytes of HBM because we wanted to have all the capacity to serve these models. So just changing the balance of the machine, making sure that we had the right computation, right, even communication I didn't talk about, but even when we're looking at our scale-up networks, like we know that tensor parallelism, would have a lot of like, all-to-all traffic. How do we optimize all-to-all traffic? This is all aspects of the microarchitecture and architecture that are being tuned for something like an LLM machine rather than a Maya 100. So that's why we believe this is like almost a grounds up design
Sure.
from a microarchitecture perspective to be able to deliver to these kind of next generation use cases.
Yeah, yeah. No, that makes a lot of sense. As you're designing the 200 for this sort of new world that we're in, this sort of post GPT world, you mentioned that you've got research teams, you've got frontier teams in house that can help sort like look ahead and essentially shape your requirements. And it clearly worked because, I mean, if you're putting pencil to paper 22, 23, like we didn't have reasoning models yet then. And there was a bit of a bet that at that time, the public conversation was all about training, and
Yes.
you guys are making a big bet already at that time on inference. Do you feel like a big company making a custom AI chip like you guys actually has an advantage, say, compared to a startup, just given that you have so many like internal users who know the shape of their workloads or are looking further ahead?
Yeah, no, I do think that, when we're designing silicon inside an hyperscaler, you really have, I would use the words again, the freedom to innovate
Mm,
because you control a lot, much portion of the entire stack, right? Just going back to in November, we introduced a state-of-the-art data center called Fairwaters. And if you look at the data center, it's amazing to see how much technology came together in terms of just building the data center structures, bringing liquid cooling inside it, being able to, bring in the latest GPU gear in it, being just the amount of technology and the innovation across the stack. How do you, create a control plane that manages all this? How do you put compute and storage around it so that, it's not just about the GPUs? So you just look at kind of the layers of innovation and
mm.
freedom that you get inside a hyperscaler versus if you were just a silicon startup, it's going to be extremely difficult. So I truly believe that this is not a chip story, right? It is really how do I create an infrastructure that's
Yeah.
best suited for this efficient frontier. And silicon, although is a very important part, seems to be taking a lot of the focus sometimes. But I do want to kind of refocus it towards yes, there's obviously competitive silicon that's super important, but then how you compose it across the stack is equally important so that you can unlock the efficiency across the entire system.
Yes.
And we understand the workloads as well, right? Have the ability to really understand that workload and then codify some of the decisions across the infrastructure of all layers of the infrastructure in some ways that's an engineer's dream come true.
Yeah, yeah.
Because you got the operating system guy sitting right next to you, you've got the Azure control plane guy sitting next to you, you've got data center infrastructure operations, just a few buildings away, and so it's all one team at that point.
Yeah, fascinating. Amazing. So you are innovating you're fully vertically integrated as a hyperscaler, and you're able to innovate from the transistors all the way up through the systems and the software all the way to the data center, which is pretty cool. You're trying to be at the efficient frontier, and you internally, I guess maybe one of the flip side, one of the challenges is you probably have all sorts of customers who want to get their hands on this. So you mentioned Microsoft Foundry. There was mention of the superintelligence team, OpenAI's GPT 5.2 models, I think, might be served on it, and even using this for inference during training. And I know also, obviously, Microsoft owns GitHub, right? So there's all sorts of opportunities internally. Who decides who gets access to this, and how do they get access?
Yeah, that's a tough question, but you're right. We do have a lot of internal. I mean, I would say internal, but obviously it is for our customers. But we do a lot of internal consumption of this. So, and we are very deliberate in how we deploy capacity, which regions we deploy capacity in, where the customer demand is, and so there is a well-oiled process inside the company that looks at basically allocation of capacity.
Mm.
I'll leave it at that. And of course, as a new architecture and a new system comes into play, we would ramp it through the course of this year as well. We'll add more capacity into our fleet. We obviously will be adding other GPUs into our fleet as well. Like I said, we believe in a more heterogeneous fleet. And so depending on where we want to optimize and place the system, like we look at the shape of the workload, we look at the customer readiness, and then we are able to deploy the capacity in that form or shape. So yes, it is a tough problem. Everybody wants more capacity, everybody wants cheap capacity, but capability at the same time, and we're going to serve our customers, so that way, in a way, like it laid it out, the GitHub Copilots or any Copilot, they be able to do it through Foundry, which is more of a enterprise platform, and then able to do it with our internal frontier model trainings and inference.
Yep, makes sense. Yeah, I do not envy whoever has to make the capacity allocation
I
decisions.
do not either.
Uh,
Thank God I'm an engineer.
yeah, right, exactly. So now we've talked about a lot of first-party customers. What about third-party customers? I mean, how will they experience the Maia? Will they be renting it as bare metal, or will they just be consuming services that run on Maia and therefore maybe have a different price point compared to other alternatives?
Yeah, I think, like we discussed, a lot of it is just going to be being able to embed it into our fleet and
Mm,
being able to, in some ways, at that point it gets abstracted away, but the goodness of obviously a more efficient infrastructure flows through to the customer, right? We are going to be previewing our full software development kit. We have started working with some universities and some I would say white gloved customers, because we want to make sure that we can onboard them through our full stack. And so there's going to be a process where we actually focus first on our internal customers, but they are serving obviously external demand, but it's just more abstracted away. And then there's going to be a motion to give this in preview to a select few customers as well. And as time goes by, we will obviously, our level of maturity in serving this to a wider base will improve as well.
sure. Yeah, no, that makes sense. Especially this is only the second system in the roadmap, and this is a significant maybe like redesign from the first system, and so I can see how also there's the benefit of serving it internally, or probably a little bit slightly more forgiving customers as you're ramping it up. Let's talk. Let's jump to software. So I know that that's always like the biggest hang up when it comes to a new chip or a new system is just making it so simple that a developer can port their model or write it from scratch. I'm sure we've seen others struggle with this. You guys have seen it too. Like, how are you guys thinking about overcoming that software adoption barrier?
Yeah, no, I think the way we think about our software ecosystem is actually in some ways it's simple in the sense that you have to invest in software at the same time you're building. So in the past few years, we were not just building the silicon, but we were building a software fully developed ecosystem around it as well, right? So things like investing in Triton compiler, that was a big thrust for us because we know that we have to lower the barrier for model porting. And this is one of the, I guess, learnings that we got from Maya 100 as well, is as we put our first generation system out, now we had the time to actually go and start building. Hey, what are we learning from the system? How do we reduce the friction for
Mhm.
software developers to come on board? And we picked like two paths, right? First is how do we go in like a much more automated way from PyTorch down to Triton compilers into lowering that into Maya hardware. And we have a programming language called nested parallel programming language, or we call it internally as NPL, right? And so that would be one path where you can use the compilers and the debuggers and the profilers that come with it to be able to kind of move your models ported over. But we also had the ability to actually create a standard kernel library. And what that standard kernel library does is it takes the most used operators that are in our models today and it populates them. And they are very performant kernels because we have
Mhm.
experts that understand the microarchitecture who are writing this at the closer to the bare metal, and they're able to populate a very strong, robust kernel library. And we know that most of the performance is actually determined by these kernels
Mm.
as we profile our models. And so that has given them, we have the option to say, hey, you are a ninja programmer, you really want to go down? Absolutely. We have a full tool suite. We have the Maya simulator. I know we have all of the work that you knew. You can run a JSON trace into a model, look at how things are progressing, but that requires a more sophisticated programmer to go down. So we have done that heavy lifting for a lot of the operators already. It's an optimized kernel library that will be available in the SDK as we preview it. And so for operators that may not be there, you have the Triton compiler path. So we made sure that we made those investments. And so you're right, this is not just about getting the silicon and the system into the fleet, but reducing that friction, and the model porting speed is going to be super critical
Yeah,
for adoption.
that makes a lot of sense. Because of course, yes, you will have benchmarks and on paper the chip looks exciting, and of course developers have to get their software to run, but then they have to extract all of that performance that's sort of latent in that system. And it sounds like you guys are working hard to have optimized kernels to help them extract
Yeah.
that.
And even before silicon arrived, we invested in a significant amount of what I'll say pre-silicon environment,
Mm,
right? And that pre-silicon environment was a combination of simulators and emulation, and so that really helped our developers, our internal developers, to be able to build these kernels way ahead of time, even before silicon came. And then when silicon came, they were off and running because they had a very, a very sophisticated environment to work in.
nice.
So that was a very deliberate, again, very intentional investment that we done because we knew that if you wait till silicon to show up and then we hey here software go build on it, it was just take another, and these systems that don't have a long shelf life like this. The
Yeah.
innovation engine is super fast, and so if you spend 6 months trying to optimize software on it, you've lost a
It's
significant portion of the system's useful life.
yeah.
And so that's a very important aspect of how do we enable our own developers with the right infrastructure and tool set ahead of when silicon comes by.
Interesting. Yeah, that makes a lot of sense. Investing to make sure that software is ready to go because to your point, yes, the cadence is so short these days, shelf life, you're right. And so I know you guys, you said multi-generational, you're already thinking about Maya 300. So like given where you're at in your roadmap, what is a measure of success? Like how will you deem Maya 200 was a success as you're moving toward Maya 300?
Yeah, no, measure of success for us, again, going back to how have we changed that economics for AI inference, right? How have we made sure that we've covered that efficient frontier? And today we know that there are opportunities for us for certain class of workloads, for certain applications, for certain customers to really drive the price point to where there'll be increased adoption. there'll be more usage and consumption, and more, I would say, innovation in it. I come from a semiconductor background, and I've worked in building chips, and I've seen Moore's law kind of play out over years, and I've seen how Moore's law has not just driven down the cost of the transistor, but it has enabled new industries,
Yeah.
right? Starting from PC to mobile to now AI, and so I believe that really as an industry as a whole, this innovation cycle in silicon and systems is really what's going to drive a completely new industry and new innovation cycle in AI.
Mm.
So maybe I'm talking a little more philosophically. That's success as a whole for our industry is to be
Sure.
able to. Now for us, I mean, we are being pragmatic about it. We have a lot of enthusiasm on the system. So we're bringing in a lot of models on it, on a completely end-to-end models are running on it. We are populating different use cases or lighting up different use cases. And this helps us kind of ramp up capacity, ramp up usage throughout this year. But it also flows into the multi-generational roadmap like Maya 300, right? This gives us that on-ramp to Maya 300 because then that will be another faster, acceleration. So what we would like to see is, yes, we had the Maya 200 ramp and we had a faster Maya 300 ramp, and more, I would say, the shape of the fleet, the economics of the fleet is continuing to shift towards a more efficient point.
Sure. As 200 ramped fairly quickly, you made a lot of changes from the 100. You've ramped 200 quickly. You're innovating full stack up and down the system. Do you expect the 300 to be sort of less drastic of architectural changes, which we'll get into the architectural details, but do you expect that those ramps will be easier? Like, for example, you said you invested in all this simulation and kind of pre-silicon testing.
Yeah, we do. We do. I mean, one thing about architectures is you don't change architectures dramatically every generation.
Yeah.
There is a lot of value in that strong foundational stability. And when you have that foundational stability and you innovate on top, so Maya 300 is obviously, we're not talking about Maya 300 today, but it is coming with a lot of innovations. But it is also coming up on a very strong, inherently stable foundation that you're going to build up. So from a developer standpoint, it is going to be, a lot easier to move faster. And a lot of that obviously will be abstracted away in terms of just better performance, better cost efficiency. So yes, that's kind of where we are approaching this from is we don't believe in making architectural right-hand turns every time and shifting the entire ecosystem. There's 100% value in being able to build up on a strong foundational base. So
Yeah.
we believe Maya 200 is that strong foundational base for us to
Th-
continue
that
to leapfrog from.
Yeah, and that totally makes sense. And that sort of implicitly suggests that you believe that today's workloads will still matter in the future with the Maya 300 generation.
Yes, yes, absolutely. I mean, we still see that, this transformer kind of models and the ability to, I mean, there is going to be refinements, there is going to be new techniques coming from research, right? But, the architecture is built in such a way that you're able to continue to take those into your current architecture. I do believe that that's not going to be an issue for Maya 300. Or in some ways, many of us who are building hardware have to place those bets, whether it's a
Yeah.
third-party merchant silicon, whether it's another hyperscaler building. We've got to look at the headlights, and I know that crystal sometimes can be foggy and new research can pop up, but we're still confident that you can continue to scale with the kind of transformer technology we have in our models today.
Yep, makes sense. Makes sense. So, you talked about cost efficiency, and I think one of the headlines in the blog and the announcements was 30% better price performance. And specifically, Scott Guthrie had called it the most efficient inference system Microsoft has ever deployed. And so I was curious if we could get into a tiny bit more of those like benchmarking details. Like, was that for small 70B models? Was that large 1 trillion parameter models? Like, what workloads is that? Because 30% is a lot. And comparing it to like your fleet, I know Microsoft has NVIDIA GPUs, you have AMD GPUs. And so this is a very sort of like intriguing statement. So I just want to unpack it a little bit.
Yeah, yeah, no, absolutely. I think what we do is we look at different use cases, right? And if you look at it like time to first token, right? You could have something that's extremely sensitive, less than a second. You could sweep it to about 10 seconds also, depending on what use cases, like we talked about summarization use cases, or you want to do something in the night, come back in the morning, it's ready. So we've kind of swept across that. We've also looked at like SLAs for like time between tokens. Is it 20 millisecond? Can it be actually more strict, like 10 millisecond? I do believe that the way you shard the model is driven by your application,
Mm.
right? So the what we do from at the system level is we give the ability for the system to or the next level up to say, hey, this is kind of my use case, and then we have some unique topology requirements, like or not requirements, but topology choices that we made. Like, hey, we have a fully connected quad, so tensor parallelism in Ford works really well, and then you can move to expert parallelism inside the rack, and so that's how we kind of are able to serve that point that the customer or the application needs. All right. So when we claim 30%, we have actually, in some ways, done this hardware software co-design to say, hey, this chip here or this system has been cost optimized. You brought out, hey, how are we making some changes? Well, we have not invested in a scale out network,
Yeah.
right? We have invested in inference driven chip. We have invested in uh, kind of taking a scale up approach more than a scale out approach. That's brought our costs down. We have kept our wattage to just 750 watts. That's brought our costs down. So it's a combination of really hardware software co-design to extract the best, token output for that particular SLA or capability. And then you look at the cost structure of the system compared to whatever we have deployed in the fleet, and that's significantly lower. And you pull those two together, and that's where you get the 30% perf per dollar advantage.
Gotcha.
So it's yeah, it's about making those right choices so that you know that if we were trying to build the most performance system in the world, we would be making very different choices,
Mm.
right? We would be pushing the TDPs up to very high, we would be pushing a lot of other system, and then we're saying, oh, and if you're trying to do training and inference both, then there will be another set of choices that we would have made. And so those are, paths that we pruned out early on so that we can hit that 30% perf per dollar.
I love it. Okay, that's a perfect segue for me too. So thank you. So let's get into those technical trade-offs you made to unlock that
Yeah.
30% per dollar. You let's talk networking because you mentioned no scale out and a big scale up domain. And I think the blog post said 6,144 accelerators was the size of the scale up domain. And so like tell us more, why no scale out? Why such a big scale up?
Yeah, yeah, absolutely. I mean, when we studied inference patterns, we've seen that a lot of our inference, like, how many devices or accelerators you need for inferences, actually could fit well within the rack, right? But when you think about as an operator, right? Because we are an operator of the system, we are deploying it for our customers. We don't want customers to be limited by, hey, you got to try to fit inside the rack, or if it
Mm.
spills outside the rack, suddenly you have a very thin pipe, and everything kind of slows down. So what we did was we said we will have a two-tier scale up, and that gives us the ability to actually take different jobs and place it across the cluster and still have the ability to communicate at a relatively good performance, right? So that's where we kind of decided that we won't do a scale out network, but instead invest in an innovative scale up, which is it's got its own AI transport layer. So although we use, we had this principle, we don't want to use anything custom or proprietary at the, so that our supply chain gets more efficient. So
Mm.
that's why you're using commodity switches, we're using, Ethernet cables and switches. But then we said we can innovate at the transport layer when two Mayas or two accelerators talk to each other, right? And so those were the innovations we put in our scale up network. And we were able to basically say, yep, we are able to reduce cost here, but still make it a high performance, highly reliable scale up network that can scale up to 6,000 accelerators. And that gives the flexibility to the operator to place the jobs that they would like to in a way that doesn't constrain them, right? And so you get a lot more available nodes and available
Mm.
accelerators to work with. Now we know that none of the inference models today are going to need 6,000 accelerators, right? They're going to mostly fit into maybe 32 devices or 48 devices, depending on how, constraints that you apply on them. But the ability to span across a larger cluster gives you the flexibility to place the jobs or sprinkle them across the cluster and, ease your bin packing problem.
Yeah, sure. Makes sense. Yeah. And of course, since you guys are operating all these, you definitely have to think about how to get as much utilization even
Exactly.
across different workloads as possible. So that's super interesting. Now, you mentioned uh, keeping the switch, efficient and maybe multi-vendor possibilities, but you talked about scaling up with Ethernet and innovating the transport layer, which sounds a lot like SUE, Scale Up Ethernet T, or eSUN.
Yeah.
Um, are you guys using eSUN? Are you not?
No,
Enlighten our
that's a
readers
great question
or
because
listeners.
when we started on this journey, eSIM didn't exist,
Right.
right? And we saw the need that, hey, look, Ethernet is a perfectly capable, ecosystem to rise up to the scale up challenges, right? And that's why we believed, and obviously it's a multi-vendor ecosystem. You have a healthy market. Your supply chain is much more healthier. You can also say that with Ethernet, we say, oh, wait, but I think we're not trying to build an Ethernet that's across 10,000, 20,000 endpoints or millions of endpoints,
Mm.
right? A scale-up domain actually has a certain, I would say, criteria that you're optimizing for. So why don't we bring that smarts and Ethernet fabric together? And that's where we started on this journey where we said we're going to keep everything standard and, non-proprietary, and then we are going to only innovate on the transport layer. Now, that thinking, that philosophy is actually what eSUN is also. So we have been working very closely with our partners. We were a very active contributor to OCP last year when we actually announced eSUN with our partners, because we actually truly believe in that philosophy, because
Mm.
that's how we've been designing our systems. And so we were very happy to see the eSUN motion come across. It says, yeah, now all you need to do is, if there is a set of features that we believe are important for optimizing at the switch level, let's bring everything together. Let's bring those people together, make those changes, and then let the, you know, XPU people or the accelerator people continue to innovate at the transport layer. So you kind of get the best of both worlds in
Mm.
that sense. You get features into your switch that are agreed upon by a community in an open fashion, nothing proprietary there. And then if you want to innovate at the transport layer, if I want to innovate or some other even wants to innovate, you can still have innovations at the transport layer. So that kind of demarcation keeps the ecosystem healthy, but also innovating.
I like it. Interesting. Really interesting. I like the
Yeah.
philosophy. Now, kind of related, you did. I feel like I saw somewhere that the NIC is integrated onto the die,
Yeah.
and so there's like a little bit of a different decision there. And so was curious if this is like any sort of IP related to the Azure Boost DPU, and why you chose not to have like a NIC on the board, but to actually integrate it into the die.
Yeah, no, it comes down to, we were extremely cognizant of cost and power. Like if you like look at a system, you will see that, the operating cost or the OpEx portion of a system in the fleet is pretty high too, not just the capital
Mm.
cost, like, not just when you purchase the system, but when you run it for 6 years. And so we were very, I guess, diligent about extracting every watt from the system, and that's where we get that, cost and power efficient point. And we believe that with external NICs, we were adding a lot more cost into the system, and that's perfectly fine if you wanted to scale out to a lot, thousands of accelerators for training. But we thought that it was not needed for inferencing, and so we did build a very, you know, I would say, optimized on-die network controller that is Ethernet based, but that's also optimized. Like we don't like buffer or anything like that. Like, so we have an extremely small area and power that goes with the NIC. We use our on-die SRAM, which is, we've invested in a much bigger SRAM to keep the packets. So if there's congestion, right, typically what Ethernet switches do or anything, they will try to create a buffer inside the NIC. But we would say, hey, we've got this large SRAM. Let's be smart about it. Let's use the SRAM to store some of the packets and things like that, and then pull directly from the SRAM. So we built some specialized DMA engines to do that. So there was like a real thought behind how we are going to optimize the cost and the power of the scale-up network. At the end, we still have 1.4 terabytes of scale-up bandwidth, unidirectional scale-up bandwidth coming out of every chip. So that's extremely well provisioned, but we do it at extremely low cost and power. Right? And then we use Ethernet switches and Ethernet cables, which again brings the cost down. So that's kind of the thinking behind integrating the NIC and having a scale-up domain that's not proprietary.
This is good. This is really good. This is very illustrative of the type of decisions that can be made when you're optimizing specifically for a certain class of inference workloads. Now, you mentioned the large SRAM, so let's transition to memory. Tell us about the memory hierarchy decisions that you made and why you chose the SRAM, why you chose a certain capacity and bandwidth for your HBM. Tell us more.
Yeah. In fact, the entire memory subsystem was really designed ground up for LLMs, right? One thing we know in inference is actually the system may not be flop limited. It may not be, compute bound, but it actually might be memory bound. And so it was very important for us to get to the best HBM technology that we find at that time. It was HBM3E, but it was also important to increase the effective bandwidth of the HBM3E. And what I mean by effective bandwidth is if I can reduce the pressure on the HBM by smart innovations on my silicon, then I can get a better output out of the chip and the system, right? And so this is where we kind of invested in SRAMs. And what that SRAM does is, because of the way our programming model is, we give explicit control to the compiler or to the programmer to actually pin the data where they want to be, and the data locality helps. And so when you have a lot more data sitting on die, you don't have to go to the HBM all the time, right? So that's one reason why we actually invested in a much bigger SRAM, because it kept. And then the bandwidth on die is about 80 terabytes per second. But if you go to HBM, it becomes 7. Like it just changes like a order of magnitude, right? And then if you go from HBM to some off-chip, some other accelerators HBM, it will reduce even more. So thinking about the data locality, the picojoule per bit of data movement was a very key consideration in some of these design choices. So that's why I think the combination of our programming model and the way the programmer can utilize this on-die memory, and then the microarchitecture and silicon innovations that went with the on-die memory, how we have partitioned it across big clusters, across some tiles. So we have an advanced network on chip that actually connects these SRAM modules with our compute modules so that the data can move between compute and memory on die much faster. These were some of the innovations that we did on chip to be able to really, in some ways, the ultimate motive is how do I get more tokens out of the chip, right? Out of the system.
Yes.
And how do I increase the effective bandwidth of the HBM? Because everybody has access to the same HBM technology. So these innovations differentiate us in being able to get to a much better optimization.
Interesting. I like to hear how you're thinking about designing your memory so that you can have memory as local as possible to the compute as you can to minimize data movement to increase effective bandwidth. This is super interesting. Now, it feels like a little bit of a new mental model for programmers or developers. Like, how much will they have to learn? Is there like a learning curve here, or does can the compiler handle a lot of this and just take advantage of it?
Yeah, the compiler is extremely sophisticated. I think the team has done an excellent job over the last 2 years to really build this out through. And like I said, I think there are 80-90% of the performance of the model is actually dominated by a few operators, right? How do you run gem? How do you run attention, different attention mechanisms, and things like that. So we are able to really kind of ease off that burden because we have an optimized kernel library that we have populated. we are of course happy for programmer like real programmers who want to extract every percentage of performance out of the system. We have given them full kind of access and capability to go and program at the nested parallel language level, the NPL level. And so I think we have a good balance here between programmers who just want to port something very fast and get running, or programmers who want to spend the time really going down.
Mm.
And even then you can either rely on your or optimized kernel library, or if you want to do some operator fusion, or if you want to do some kernel programming, we will support you in that, right? We will give you the tools, we'll give you the visibility into the architecture. We have a simulator that you can use. We can give you all the traces. You can extract all the traces that you need to really get to that performance point.
Nice. So given that you've got all that SRAM and the HBM, and you're giving developers tools to kind of go crazy if they want and get and just really like eke out all the optimizations to reduce latency as far as possible, I have to ask, like, zooming way out, right now what's hot in the news is like these SRAM only type chips that are sort of like hyperspeed, super low latency. Do you feel like that you guys have the right architectural design so that people could start to get that level of like really low latency given how much SRAM is at their disposal?
Yeah, I think it comes down to, like, again, the system choices you have made, because we've seen some architectures that depend a lot on SRAM but don't have a memory hierarchy or don't have the right HBM behind it. We've obviously seen some very innovative, very exciting products in the market. You obviously have the wafer scale engines. So I do think, and going back to what I believe is in, like, if you are really optimizing for a certain class of workloads, like extremely low latency, but everything is staying in your SRAM. You don't have to go, your model doesn't, spill out of the SRAM. There is a use and need for those kind of applications in your fleet. Those are great architectures. We've tried to become a little more broader in that sense. It's like, hey, maybe the word I want to use is that we're not as brittle sometimes, right? We can actually expand a bit and say, hey, this might be the class of workload that we want to optimize for. This has a little more of that ability to have a large enough SRAM to pin the data that we need. But if you have to go outside those boundaries, we have an HBM, basically memory subsystem that we are serving with an extremely, fast on-chip NOC. We have specialized DMA engines to go out on scale up and go towards HBM sitting in somebody else's, data sitting in somebody else's HBM. So we give that the system is actually broader enough to be able to absorb those use cases. So absolutely, I think there is a need and a reason for those architectures to exist, but they have a certain criteria under where they perform well and certain criteria where they may not perform well.
Yes, I hear what you're saying. So, okay, this is a perfect segue again. So you talked about you've got SRAM, but you can spill over into HBM, which the chips that don't have any HBM, they can't do that, right? So they're perfect for if it all fits in SRAM. You've got the HBM, you've got the ability to reach into other accelerators through the scale up network to get to their HBM if it's like a really large model. Now, another sort of hot thing in the news lately has been that context memory storage from NVIDIA, where you actually can offload out. If it doesn't fit in HBM, you can offload to like flash SSDs or something.
Mhm.
And that, of course, the use case there is like really long context and managing KV cache. Tell me about like really long context workloads with the Maia. Like you've got access to lots of HBM. Do you ever see needing to like offload KV cache, or how are you
Yeah, no,
thinking
that's
about it?
that's a great question, and it comes down to, like, how you're using the system, right? So obviously, if everything needs to be really hot KV cache, then you want the data to be in your HBM. And what you would do is, based on your model size, based on the SLA that you want to deliver, you would shard the model between, maybe, if you want to deliver an extremely high, um, or extremely fast response, like time between tokens is, let's say, 10 millisecond, right? What you would do is you would actually take the model and shard it or divide it across a lot more accelerators, right? That way you are using the HBM bandwidth of a lot of accelerators, right? At the same time, if you relax that to 20 milliseconds or something above, you say, hey, I don't need to use 32 accelerators for this. I can do it in 16. And sometimes if you relax it even more, I could do it in even less time. When you relax the HBM, what happens is that you can actually do it in much fewer accelerators. So that's kind of the hot KV cache. Now there's also a use case where it is a warm KV cache. Let's say the users are not in there. It's like a session, right? And you go back and you come back in and you want to load up the session again. This is where you don't need to keep the data in your HBM. What you can do is at that point, you can keep it in a second tier of memory. So we have a head node, and in that head node, we have provisioned, DDR memory. We have SSDs in that head node, and then if it's another tier, we also have like the Azure Boost in our system, which can go over kind of a network and pull data out of a blob storage or a storage, an Azure storage account. So we have this tiering of memory systems where we have the HBM, we have local DDR and local flash, and then we can actually go over Azure Boost, which is optimized for remote storage and pull data in from the remote storage as well. So we kind of thought through like, hey, how does the user, how does the application want, where is the data locality of that is needed? If it's needed on die, on the package, is it needed in the system but close enough? Or you can tolerate the latency of pulling something from further out.
Nice. Awesome. Well, thank you for the education. That was very interesting. I know we're bumping up on time. So last question. I saw the blog said that these were getting deployed near Des Moines, Iowa, and that's exactly where I live. So when can I come take a tour?
Oh yes, absolutely. Anytime. In fact, maybe we'll ship a rack to your house.
Hey, there you go. I've got an extra bedroom. I'll plug it in.
It just
I saw it can be air cooled. It can be air cooled.
It can be air cooled. Just make sure you have the right power.
True. Yes, I definitely don't. Yes.
So
awesome.
it was great chatting. I appreciate all the questions. Appreciate getting us the opportunity to talk about Maia 200. It's an exciting product for us. Obviously this is a multi-generational journey, but we truly believe that this is the kind of innovation that changes the curve of AI inference economics, and we're going to be on it.
I love it.
The efficient frontier curve.
Awesome. Very exciting. Congratulations to you and the team. And let's stay in touch. Come back again in the future and update us.
We would love to. Thank you, Austin.
All right. Thank you.